This video is how to find limits algebraically. So we have a few different methods for this. The first method is by direct substitution, and this would be that ideal case where the limit at a certain point is exactly the same as when you evaluate it at that certain point. So that's saying the limit as x approaches a value a of the function f of x is exactly the same as if you just plugged in a. So for example, we're going to find the limit as x approaches 5 of the polynomial function 2x squared minus 3x plus 4. So you'll notice when we look at this function, this polynomial function, there's no sort of limited domain here. 5 is in the domain of the function. And so I'm just going to go ahead and evaluate the function at 5. I have 2 multiplied by 5 squared minus 3 times 5 plus 4. And you can do that in your head or plug it into a calculator, and either way you would get 39. So that means that the limit as x approaches 5 of the function is 39. Another method for finding the limit algebraically is to factor the problem. So here we're going to do an example. We're going to find the limit as x approaches 1 of the function x minus 1 divided by x squared minus 1. And if you look at this problem, you will notice that 1 is not in the domain of the function. If I put a 1 into this x on the bottom, I've got 1 squared minus 1 is 0, and that's a problem. You can't take a fraction and divide by 0, so 1 is one of the values that's excluded from the domain of this function, which is the problem with finding the limit here. We can't do direct substitution because of that. So what we're going to do instead is we're going to factor. The top of the equation, the expression, is going to stay as x minus 1. The bottom can be factored using the difference of squares. So that's going to give me x plus 1, x minus 1. And what I notice here is that these two factors cancel out to make a 1. So top and bottom cancel out to make a 1, so I'll leave a 1 in its place. That leaves me with 1 over x plus 1. So what I'm looking at now is 1 over x plus 1. If I want to evaluate this and use direct substitution at 1, now it's possible for me to do that. So now I can say I'm going to plug in 1 to what I had left over. And that gives me 1 over 1 plus 1, which is 1/2. So the limit as x approaches 1 of the function is 1/2. All right, here is the next method. We can expand a problem to see if that will help us. So here's an example. We are going to find the limit as x approaches 0 of the quantity x plus 3 squared minus 9 divided by x. And here again, you'll notice 0 is not in the domain of this expression. We cannot plug 0 in. It's undefined there. So what I'm going to do, I can't do any sort of canceling with the way it's written right now, so I'm going to expand that x plus 3 squared. And I need to FOIL this out, so that leaves me with x squared plus 6x plus 9. And I still have that minus 9 on the end, divided by x. And I can see that those two 9s are going to cancel. And at this point, now I can go ahead and factor what I had left over and kind of treat it like the last example we had. So if I have x squared plus 6x, I can factor a GCF of x out, and that leaves me with x plus 6 on the top. And then on the bottom, I just have another x. And now we can see that these x's cancel to make 1, and so that simplifies to just x plus 6. Now at this point, I am able to evaluate this problem at 0. So now I'm going to plug 0 into this leftover expression, and I get 0 plus 6, and so that means that 6 is what I have there. So the limit as x goes to 0 of that original function is 6. So the limits that we are usually interested in are not the ones where you can plug the number directly in. We're usually interested in the ones that we're going to have some issues with. All right. The fourth method is to rationalize. So, for example, if we want to find the limit as x approaches 0, the square root of x squared plus 9, take away 3, divided by x squared. Again, you will notice that 0 is not in the domain of this function. You cannot plug 0 in and have this be defined. So that's the issue here. So we're going to take that original rational expression and we are going to multiply it by its conjugate. So I'm going to take, and the conjugate looks real crazy, but it works out kind of nicely. So the square root of x squared plus 9 plus 3 over the same thing. So on the top, I'm going to have to FOIL this. I have the square root of x squared plus 9 multiplied by the square root of x squared plus 9, and that leaves me with just x squared plus 9. And then I have the square root of x squared plus 9 multiplied by 3. And then I have negative 3 multiplied by that. And then I've got negative 3 multiplied by positive 3. And then on the bottom, I'm not actually going to multiply this out. I'm just going to leave it. And you will see in a second why I just left it, what that will do for our problem. Okay, so now we can do some simplifying here. I can see that this positive 3 times square root of x squared plus 9 and the negative version cancel out. I can also see that this positive 9 and this negative 9 are canceling out on the top. So that leaves me with only an x squared on the top. And then on the bottom I have x squared multiplied, oops, that is not what I meant to write, multiplied by the square root of x squared plus 9 plus 3. And at this point we can see that these two things would cancel out to make a 1. So I'm going to leave a 1 in its place. Divided by square root of x squared plus 9 and a plus 3. And now we're at the point where we can actually evaluate this at 0. So I'm going to go ahead and do that. So I have 0 squared plus 9 is just 9. The square root of 9 is 3. So the limit as x approaches 0 of that original function we had is 1/6. We have another method. I promise there's not a million, there's just 2 more. So undo complex fractions, that's another thing we can do. or a better word might be to simplify the complex fraction first. So here's our example for this one. We are going to find the limit as x goes to 1 of 1 over x minus 1 divided by x minus 1. So again, in this problem, you'll notice 1 is not in the domain of the problem. If we did 1 minus 1 in the denominator, that would make this expression undefined. You'd have an error. So we're going to go ahead and use what we know about fixing complex fractions. So I have 1 over x minus 1 divided by x minus 1. And the only denominator we have in this problem is the x. So that means that to fix this complex fraction, I just need to multiply the entire problem by x over x. So if I take this x on top and distribute it, 1 over x multiplied by x, the x's are going to cancel, I'm just going to get 1. And then x multiplied by negative 1 is negative x. On the bottom, I have x multiplied by x is x squared. X multiplied by negative 1 is negative x. All right, now at this point, hopefully you're seeing, again, I still can't plug in 1. That would be a problem still. It's still outside the domain. So now I'm going to go ahead and factor the problem. I know that the numerator needs to be in the correct order, so I'm going to rewrite this as negative x plus 1. And I can go ahead and factor the bottom already. I have a GCF of x there that I can take out. So take out that x. That leaves me with x minus 1 in the denominator. And now in the numerator, if I can factor out a negative 1, then you'll see that some canceling can happen. So factor out the negative 1, that leaves me with x minus 1. And then on the bottom, I already had x times x minus 1. And now we can see that we have factors that are canceling to make 1. That leaves me with negative 1 over x. And at this point, I can evaluate this function. So if I plug in 1, negative 1 over 1, overall that's going to equal negative 1. So now I can conclude that the limit as x approaches 1 of this complex fraction is negative 1. All right, now in most of these examples, in fact, I think in all of them, we knew that, well, all of them except for the first one. In all these except for the first one, we had something that was outside of the domain. And if you look at the problem, we canceled factors there. We canceled factors here in the third example in the expanding problem. In the rationalizing problem, we canceled out factors here. And then in undoing complex fractions, we canceled out fractions here. So that means that in every single problem, except for the first one, when we had direct substitution, in every single problem there was a hole in the graph. So limits always exist at those holes. When we have a hole in the graph, that's unless it's a piecewise, that's a different story. But in this sort of situation, limits are going to exist at the hole. If there are not factors to cancel, you're going to use substitution to find the left and the right hand limits. All right, so our note to ourselves is that when factors cancel, there was a hole. And when there's a hole in the graph, I can't say this with absolute certainty, but for the most part, when there's a hole in the graph, the limit exists, and we're going to be able to find it, with the exception of some interesting piecewise functions that we have. If there aren't factors to cancel, that means there isn't a hole, then we're going to use substitution to find the left-hand limits and the right-hand limits and see if they agree. So if your goal is to plug in 4, and you can't do that because it's outside the domain, then plug in 3.999 and 4.001, the left-hand limit and the right-hand limit, and see if they agree with each other. And if they do, then you have a limit there.